Let's see if we can find the limit as theta approaches 0 of 1 minus cosine theta over 2 sine squared theta. And like always, pause the video and see if you can work through this. All right, well, our first temptation is to say, well, this is going to be the same thing as the limit of 1 minus cosine theta as x approaches, or not x, as theta approaches 0, of theta as theta approaches 0, over the limit as theta approaches 0 of 2 sine squared theta. Now, both of these expressions, which could be used to define a function, they would be continuous if you graphed them. They'd be continuous at theta equals 0. So the limit is going to be the same thing as just evaluating them at theta equals 0. So this is going to be equal to 1 minus cosine of 0 over 2 sine squared of 0. Now, cosine of 0 is 1, and then 1 minus 1 is 0, and sine of 0 is 0, and you square it, you still got 0, and you multiply it times 2, you still got 0. So you got 0 over 0. So once again, we have that indeterminate form. And once again, this indeterminate form, when you have 0 over 0, doesn't mean to give up. It doesn't mean that the limit doesn't exist. It just means, well, maybe there's some other approaches here to work on. If you got some non-zero number divided by 0, then you say, okay, that limit doesn't exist. And you'd say, well, you'd just say it doesn't exist. But let's see what we can do to maybe think about this expression in a different way. So if we said, so let's just say that this, let me use some other colors here. Let's say that this right over here is f of x. So f of x is equal to 1 minus cosine theta over 2 sine squared theta. And let's see if we can rewrite it in some way that at least the limit as theta approaches 0 isn't going to, we're not going to get the same 0 over 0. Well, we got some trig functions here, so maybe we can use some of our trig identities to simplify this. And the one that jumps out at me is that we have the sine squared of theta. And we know from the Pythagorean identity in trigonometry, it comes straight out of the unit circle definition of sine and cosine. We know that sine squared theta plus cosine squared theta is equal to 1. Or we know that sine squared theta is 1 minus cosine squared theta. 1 minus cosine squared theta. So we could rewrite this. This is equal to 1 minus cosine theta over 2 times 1 minus cosine squared theta. Now, this is a 1 minus cosine theta. This is a 1 minus cosine squared theta. So it's not completely obvious yet of how you can simplify it until you realize that this could be viewed as a difference of squares. If you view this as a squared minus b squared, we know that this can be factored as a plus b times a minus b. So I could rewrite this. This is equal to 1 minus cosine theta over 2 times, I could write this as 1 plus cosine theta times 1 minus cosine theta. 1 plus cosine theta times 1 minus cosine theta. And now this is interesting. I have a 1 minus cosine theta in the numerator, and I have a 1 minus cosine theta in the denominator. Now we might be tempted to say, oh, well, let's just cross that out with that, and we would simplify it and get f of x is equal to 1 over, and we could distribute this 2 now. We could say 2 plus 2 cosine theta. We could say, well, aren't these the same thing? And we would be almost right, because f of x, this one right over here, this is defined, this one right over here is defined when theta is equal to 0, while this one is not defined when theta is equal to 0. When theta is equal to 0, you have a 0 in the denominator. And so what we need to do in order for this f of x, or in order to be for this to be the same thing, we have to say theta cannot be equal to 0. But now let's think about the limit again. Essentially what we want to do is we want to find the limit as theta approaches 0 of f of x. And we can't just do direct substitution into, if we really take this seriously, because we're going to like, oh, well, if I try to put 0 here, it says theta cannot be equal to 0. F of x is not defined at 0. This expression is defined at 0, but this tells me, well, I really shouldn't apply 0 to this function. But we know that if we can find another function that is defined, that is the exact same thing as f of x except at 0, and it is continuous at 0, and so we could say g of x is equal to 1 over 2 plus 2 cosine theta. Well, then we know this limit is going to be the exact same thing as the limit of g of x as theta approaches 0. Once again, these two functions are identical, except f of x is not defined at theta equals 0, while g of x is. But the limits as theta approaches 0 are going to be the same. And we've seen that in previous videos. And I know what a lot of you are thinking, Sal, this seems like a very, why don't I just, do this algebra here, cross these things out, and then just substitute 0 for theta? Well, you could do that, and you would get the answer, but you need to be clear, or it's important to be mathematically clear of what you are doing. If you do that, if you just cross these two out, and all of a sudden your expression becomes defined at 0, you are now dealing with a different expression or a different function definition. So to be clear, if you want to say this is the function you're finding the limit of, you have to put this constraint in to make sure it has the exact same domain. But lucky for us, we can say if we found another function that's continuous at that point that doesn't have that gap there, that doesn't have that point discontinuity out, the limits are going to be equivalent. So the limit as theta approaches 0 of g of x, well, that's just going to be, since it's continuous at 0, we could say that's just going to be, we can just substitute. That's going to be equal to g of 0, which is equal to 1 over 2 plus cosine 2, 1 over 2 plus 2 times cosine of 0. Cosine of 0 is 1. So it's just 1 over 2 plus 2, which is equal to, deserve a little bit of a drum roll here, which is equal to 1/4. And we are done.